Hi everyone! For today we are going to talk about some interesting compiler optimization, and one of them is called profile guide optimization. It's a data-driven optimization that helps to optimize your software based on some runtime statistics, and trust me, it can help you to achieve really impressive performance results for your applications. A few words about me. My name is Alex. I'm a CTO at Zaitsau company. My experience regarding profile guide optimization is that during the last 2 years and a half, I optimized tens, maybe up to 100 projects with PGO. I'm crazy about performance. That's why I like this conference. I'm especially interested in different compiler optimizations, more precisely hardware-independent compiler optimizations. And besides IT, I like hiking and playing video games. So before the start, I want to share with you some benchmarks regarding performance boosts that can be achieved by applying PGO to the real software. Here we see databases, compilers, interpreters, network proxies, log shipping solutions, browsers, and for all of them, PGO can help you to achieve really impressive performance results, and that's why I really like these optimizations and wanted to share with you my experience. So let's begin. So before the start, we need to make a quick overview about the regular build optimization pipeline. Actually, there are two major schools about how our application can be compiled. The first one is called ahead of time optimization, ahead of time compilation. Here we see you have a regular CI/CD pipeline, the CS, and the regular compiler. This compiler takes a source code and compiles to a machine code, a native code, and this machine code is deployed to a target machine where it's executed. Another option is use a just-in-time compilation model, where we have the same CI/CD pipeline, the compiler, and as a result, instead of a machine code, we have some kind of bytecode that is delivered to a target machine and where it's executed in some kind of a virtual machine. So we're not going to talk about interpreters because they are not so efficient and performant for this conference. So all modern compilers, good compilers, perform a lot of optimizations inside, like inlining, hot-cold code splitting, loop roll-unrolling, some more advanced things like link time optimizations, many other things. We're not going to talk about them for today, but we need to know one important thing. Many of these optimizations, especially inlining, can benefit from providing to the compiler runtime information about how your application is executed, how frequently which branches are executed, where some cold code is located in your application, and so on. And here we see a problem because in the just-in-time world, we have a way to gather the statistics on a target machine because we have some virtual machine that executes our application and is able to gather the statistics. But for the ahead of time world, we don't have such a possibility because we have only a native binary on a target machine, and that's it. And the solution for this problem is called profile guided optimization. So the idea is very simple. Collect runtime statistics on a target machine in some way, pass it somehow to a compiler in our CI/CD pipeline, and use this profile during the compilation phase. That's it. There are different PGO kinds nowadays. The most basic one is instrumentation PGO that was first implemented and could be found in most compilers. The more advanced version is called sampling PGO. We will talk briefly about these two kinds of PGO in this talk. There are different flavors and combinations of them, like a context-sensitive intermediate representation PGO, like this is like a fancy modification of instrumentation PGO, like context-sensitive sampling PGO, and so on, and some really exotic PGO types like a temporal PGO. We will not talk about it for today. But for example, this temporal PGO is used for optimizing startup time of an application. So let's start from the most basic one, from the instrumentation PGO. How does instrumentation PGO work? So at first you need to compile your application in the instrumentation mode. What does it mean? In the instrumentation mode, compiler automatically inserts into your application some additional machinery that helps to collect the runtime statistics about how your application is executed, like which branches are executed, how frequently, and so on. You can think about it like a machinery for gathering coverage for the code. In many cases, this code inside compilers are reused between coverage stuff and PGO stuff. So you need to run the instrumented application on your typical workload for which you are trying to optimize your application. Then you need to collect PGO profiles somehow from your application. Usually, in the instrumentation PGO, after the exit of your application, all these statistics, like values of all counters from your application, are just dumped to a file on the file system. However, it's possible to dump it, for example, not to a file system, but to a memory buffer. It could be important, for example, in cases where you don't have a write access to a file system, like embedded case, and you even able to trigger a profile dump not at the exit point, but via some signal or some handler in your application. It's possible to achieve with some compiler intrinsics. And then you need to pass these PGO profiles to compiler, and you need to recompile your application once again with these PGO profiles. And that's it. Unfortunately, instrumentation PGO has caveats. The first one, you need to compile your application at least twice, for instrumentation and for optimization. And it could be a problem if the application is really huge, like imagine a ClickHouse or Chromium, and it can take hours to build it only once. You can imagine that your build time will be increased at least twice for instrumentation PGO, and it could be a problem for your CI pipeline, trust me. Instrumental binary is larger because an additional amount of instructions are inserted into your application, and instrumental binary is slower because an additional amount of instructions are executed in runtime. But how critical these caveats are in practice? So let's start from binary size increase table. Here we see some comparison about between release size without instrumentation and the instrumented size. It's a release plus instrumentation. And here we see quite a huge increase, but in my experience, you can expect up to 2x binary size increase in most cases. I have much more data points, and I never met the binary size increase more than 2x. And even this is not critical for most cases because disk space is cheap enough, but if you work in the embedded world, please keep it in mind. Regarding binary slowdown, the situation becomes a bit, in some cases, even terrifying, because the actual binary slowdown can be really different between applications and the training workload. For example, the most terrific case here is a ClickHouse case. The actual slowdown was more than 300 times. It wasn't a mistake. It was proved by many benchmarks by me. The reason is because the compiler inserted the machinery into the real hot loops inside ClickHouse, and these loops were executed, I guess, millions of times. That's why the overhead was so huge for the ClickHouse. For other applications, we see really different numbers, like 14x, and much less in other cases. In practice, you cannot predict it somehow without actual benchmarking. So if you want to know the real slowdown for your use case, please perform PGO training and measure the actual slowdown. Google is the largest PGO user in the world nowadays, as far as I know, met these problems many years ago, and they tried to mitigate it by implementing another way to do PGO that is called sampling PGO. How does sampling PGO work? So, at first you need to run your usual application without any instrumentation. So we don't introduce overhead into your application. Instead of collecting PGO profiles via built-in instrumentation into your application, you need to attach an external profiler to your software. Usually Linux pair for Intel vTune are used here. And the rest of the instruction is the same. You need to recompile your application once again with this runtime information, and that's it. Unfortunately, sampling PGO also has caveats. The first one is called branch stack sampling. This is a hardware feature that helps to your profiler gather more precise profiles from your application. Unfortunately, this feature can be unavailable in different combinations of hardware and software. For example, for Intel CPUs, this feature was implemented more than 10 years ago, and nearly at the same time was upstream to the Linux kernel. For AMD CPUs, this feature is called branch sampling and was introduced only since Zen 3 for EPYC and since Zen 4 for all AMD CPUs. And was upstreamed only at the last year, I guess, to the Linux kernel. ARM also has a similar feature that is called BRB, Branch Record Buffer Extension, is available in the latest ARM specification for other architectures. Please refer to official documentation. There are a lot of them, RISC-V, PowerPC, and different operating systems. So a lot of combinations. And another limitation is that BSS frequently is not properly emulated by hypervisors. So there is a huge chance that you will need to do a bare metal if you want to use sampling PGO. Another limitation is limited tooling support. Why do you need tooling? Because when you collect a profile, how your application is executed via an external profiler, you need to convert this profile to a compiler-compatible format, because your compiler doesn't understand a format from the Linux peer profiler, for example. And for doing this, there are several options. The first one is the default one nowadays, is using a Google Auto FIDO tooling. By the way, FIDO is a synonym to PGO. FIDO means feedback-driven optimization. Unfortunately, this tooling is buggy. For example, it has multiple issues with building with the latest LLVM version and so on. But it's the most complete set of tools for doing this kind of conversions. Another option is to use LLVM Prof Gen tool. It's already a part of LLVM, so no build issues expected. However, it has, at least for now, a limitation that it supports only profiles with BSS. Google Auto FIDO doesn't have such a limitation. Go compiler uses another profiling ecosystem that is called pprof. I don't have enough experience with the PGO in Go. I just play it a bit and read a lot of articles about it. and as far as I see, it works quite well, so no issues should be expected here. So let's compare instrumentation and sampling PGO. At first, instrumentation allows to achieve better optimization in general. According to Google, sampling PGO usually achieves from 80 to 90% of efficiency of instrumentation PGO. Sampling has far less runtime overhead compared to instrumentation, like nearly 2% with sampling compared to plus infinite with instrumentation. Remember the ClickHouse case. And even this amount of overhead can be tweaked. So if you want to get more precise PGO profiles and consequently more aggressive PGO optimization, you can increase the sampling rate in your profiler. If you want to reduce the overhead and get less efficient PGO optimization, you can reduce the sampling rate, and that's it. And instrumentation has better compiler, tooling, and OS support because it's easier to implement, and Google, as the main sampling PGO user, they care mostly about the Linux platform, and that's why, for example, the Microsoft C++ compiler MSVC doesn't support sampling PGO. So how should I collect PGO profiles? There are different strategies for that, but at first, please don't collect PGO profiles from unit tests. Why? The main aim of unit tests is testing your application in many cases. Most of these cases are corner cases. And I am sure that your target workload for which you are trying to optimize your application are not full of corner cases. At least I hope so. So please don't use unit tests for that. From benchmarks, actually it depends. It depends on how similar your benchmarks are to your target workload. If they are similar enough, for example, the ClickBench bench suite for the OLAP databases, you can use it for the PGO training phase. Otherwise, think about it twice. For a manually crafted training scenario, that's a good option. Actually, this option is used in all or almost all open source projects that support optimization, PGO optimization. They build scripts. How does it look like in practice? You can write a simple bash script where you can codify a simple training scenario. For example, if you want to optimize a compiler, you can write a simple scenario where you compile with your instrumented compiler a simple program, like sample with one of several files, then gather runtime statistics via PGO profiles and compile an optimized version of your compiler, and that's it. And the best option from production, that's why Google implemented sampling PGO, because they collect PGO profiles directly from production environment. But please be careful, because in this case, highly likely you will not be able to use instrumentation PGO in your directly in your production due to the overhead. In some cases, it's possible, but please keep it in mind. Let's talk about common PGO traps and mitigations for them. At first, PGO optimizes some cases and pessimizes others. The first mitigation is try to build per workload application. For example, if you have two conflicting workloads, you can try to gather two different PGO profiles and then build two different versions of your application. If it's not possible to do it for you for multiple reasons, you can try to gather multiple profiles and merge them into one, and then use this one generic PGO profile during the PGO optimization phase. In this case, probably you will not achieve the peak performance for each case, but anyway, we will still get a performance boost for your application in general. PGO build is not reproducible. Reproducibility is a hot topic nowadays, especially for the open source community. And PGO can introduce here additional problems because it's an additional input into your build environment. So the solution can be simple. Just commit, collect, gather it, PGO profile to a version control system, and then reuse this committed PGO profile during each build. And your build will remain reproducible. trust me. However, if you will do it, you can get another problem that is called profile skew problem. So when you save the PGO profile, usually your application is not static. Some code is changed, new code is added, and so on. In this case, new code will not be covered by saved PGO profile, and even the and for the changed code, your PGO profile can be invalid, and and using such a profile even can harm performance of your application. So the solution, just regenerate these PGO profiles. How frequently? It depends on your case. You can regenerate them during each build, for example, each commit, or each week, or each month. It depends on many cases. It's all up to you. And the last problem in this list, PGO doesn't help my application. It's especially true for some heavily optimized by humans application nowadays, like FFmpeg, for example. So congratulations, you found a really good piece of software, but I have one piece of advice here. So even if PGO doesn't work for this application for now, probably later, less optimized code will be added to the application, and maybe for this piece of code, PGO will help later. So if PGO doesn't work for you now, give it a try later. Maybe it will help, or maybe not. It depends. So what about current PGO state across languages? C and C++ have the majorest existing implementation in the world because Google invested a lot of money into the implementation because Google is the largest C++ user in the world. Rust, D, and other GCC LLM-based languages and compilers, almost the same as C++, but without the most advanced PGO features like context-sensitive intermediate representation PGO. It's not a critical, but anyway, and I hope someday these advanced features will be backported to these technologies too. Go, the official compiler for Go, supports PGO from the last year. It can do less things compared to C++ implementation, but Google knows a lot about PGO, and they invest money into their PGO implementation in the Go compiler. So in a few releases, I hope Go's implementation of PGO will really shine. C# supports PGO. This feature is called dynamic PGO. I am not a C# engineer, cannot say much here, but I can recommend reading the official Microsoft blog about it. GraalVM is a ahead-of-time compiler for the Java ecosystem, support Java, Kotlin, and several other technologies. Actually, GraalVM supports PGO, but not enough public available information how efficient it is in practice for real applications. Their documentation lacks a lot of details and so on. I asked many questions in the upstream, but at some point they stopped to answer my questions for some reason. I don't know why. And for other languages and compilers, with high probability, PGO will not be supported because the proper implementation of PGO in a compiler can be a difficult thing to achieve for the compiler engineers, especially the compiler is not LVM or GCC based. What about current PGO state across build systems? Because usually we don't build our software directly via invocation compiler. We use some kind of build system. Fortunately, almost no build system have built-in PGO support. As far as I know, only Bazel has some kind of PGO support in their flags. It's called FDO instrument with the optimized flags. It also has some drawbacks because, like any abstractions, it hides some PGO, the most advanced PGO stuff from you. So if you want to use it, you will need to pass compiler flags manually. Cargo is a default build system for the Rust ecosystem. Doesn't have built-in support for PGO, but it has a really wonderful extension that is called Cargo PGO, and I highly recommend you to use this extension. If you are going to optimize a Rust application with PGO, actually almost all my benchmarks for Rust applications are done via this extension. Highly recommend to use it. And for other build systems, just pass compiler switches manually. Which compiler switches according to documentation of your compiler, how to pass them, please read documentation for your favorite build system. What about current PGO state across packages and software? So not so many applications unfortunately support building with PGO in their build scripts, and consequently, in general, OS distributions don't build its software with PGO because maintainers don't want to spend their time with introducing PGO for various reasons, like reproducibility, for example, issues. However, some operating systems enables PGO for more packages like Gentoo, Clear Linux, or CacheOS. Especially can recommend CacheOS to take a look on because they are super friendly developers and they're crazy about optimizations. About optimization and about introducing PGO into their ecosystem, and not only PGO. And in my experience, you can expect that highly likely these kind of packages will be optimized with PGO. It will be web browsers, Chromium based, and Firefox. They optimized with PGO for several years, and compilers like Lang and GCC. However, as a rule of thumb, if you want to have something PGO optimized, you need to rebuild it locally with PGO optimization. What about some more advanced PGO use cases? Google not only collects PGO profiles directly from production, they collect them continuously. Google has an internal platform for collecting PGO profiles continuously based on Google-wide profiler. Unfortunately, this solution is closed source and I've never heard something about open sourcing it. There is no ready-to-use open source solution for that, at least yet. There are some ideas to implement it based on open source platforms like Grafana Pyroscope and Elasticsearch Universal Profiling Platform, but unfortunately nothing to try yet. These ideas are just discussions, nothing to try. What about good candidates for applying PGO on? Actually, any software with many branches inside. Compilers, interpreters, various developer toolings, databases, especially databases. ScyllaDB can be optimized with PGO. Different parsers, even operating system and drivers can be optimized with PGO, and many other kinds of software, including libraries. Libraries also can be optimized with PGO, static and dynamic libraries. So, regarding your optimization roadmap, you can have something like this. Release mode, obviously. Don't forget about it. Probably you can enable some CPU-specific instruction set like AVX. Please enable link time optimization before PGO because it will be easier to enable compared to PGO. By default, full aka fat LTO, thin LTO otherwise, because it's more scalable. Only after that I can recommend to enable PGO. Instrumentation by default because it has better tooling support and more efficient, and only if instrumentation doesn't work for you for some reason, try to play with sampling. And after PGO, it's possible to use more advanced things. What about more advanced techniques? We have a few time, but let's take a quick look. So, what if it's possible to optimize operating system with PGO? Like there are several benchmarks about optimizing Linux kernel and Windows kernel. So, what if we will build workload-specific operating system? For example, PGO optimized Linux kernel for databases. PGO optimized Linux kernel for network solutions, and so on. There are papers in this domain. This idea is called application-specific operating systems, and there are proofs that it can help you to achieve additional performance for your workloads. where or you can even build application-specific interpreters. I did this several times too. For example, I have benchmarks for the script-specific Lua interpreter with some positive results. Or you can try to use some machine learning-based techniques in your compiler. There is a project for LLVM that is called MLGo that introduces ML-based optimizations into the LLVM. For now, there are two of them. Machine learning-based inlining stuff for optimization for size, and machine learning-based register allocation optimization. And several weeks ago, I even met a person in the internet who uses this optimization for real applications. I was pretty impressed, to be honest. And the last but not least is the post-link time optimization, or PLO, via tools like LLVM Bolt, Google Propeller, and Intel TLO. Let's talk about them a bit, since they are similar to PGO, but they are not the same. What is it? What is PLO? The idea is pretty simple. If you have a large binary, it consists of many functions that are located in different places in the binary, because the binary is huge. So the idea is, if we place together functions in a binary that are executed frequently together, it will reduce the amount of CPU instruction cache misses, and consequently it will improve the application performance. This idea was implemented firstly, as far as I know, by Facebook engineers in the tool that is called LLVM Bolt. This tool was originally called by Bolt and was upstreamed to LLVM. That's why LLVM Bolt. This is the most major tool on the market nowadays for doing it. There are different alternatives like Google Propeller and Intel Thin Layout Optimizer, or TLO. They are less major in my opinion. So if you are going to play this optimization, please start with LLVM Bolt. CacheOS also uses LLVM Bolt for some packages. And this tool's workflow is almost the same as PGO: instrumentation phase, training, and optimization phase. And similarly to PGO, at least LLVM Bolt can also work in the sampling mode, so you can avoid the instrumentation phase. For additional details, please refer to the official documentation of these tools. So what about comparison between PLO and PGO? Why do you need both? PGO doesn't implement optimizations from PLO nowadays, and vice versa. PLO doesn't have all optimizations from PGO. That's why PLO is not a PGO substitution, it's an addition. I have a benchmark where I compared SQLite performance with PGO plus PLO versus PGO optimized SQLite and PGO only optimized SQLite and PLO only optimized SQLite. And PGO plus PLO were the most efficient combinations of all of them. So it really it's really a good thing to use these both optimizations at the same time. So your final optimization pipeline can look something like this: release mode plus link time optimization plus PGO plus PLO. And this is a really advanced optimization pipeline nowadays. So if you want to learn more about PGO, I highly recommend to visit my GitHub repository, Awesome PGO. There I collect as much as possible materials about PGO in the internet, many benchmarks, current PGO state across different ecosystems, compilers, compilers, build systems, package managers, and so on. Highly recommend to read you the client documentation about PGO. Also, if you want to ask some question about PGO, please visit LLVM Discord profiling sub-channel. You can ask directly LLVM engineers. And highly recommended to visit the CacheOS Discord, because I'm pretty sure they would be happy to share their experience about PGO with you, especially if you want to integrate PGO into other operating systems. So that's it for today from my side, and I wish you happy PGO.